Welcome to the deep dive. So I think when most people picture this era, they probably think of Isaac Newton and the apple tree.
That's the classic image.
Exactly. But today we're going to tear up that textbook term, the scientific revolution.
Yeah, that's a term very few historians actually use anymore.
We're diving into a period from, roughly 1490 to 1730, and we want to call it what it really felt like for the people living it, the intellectual age of the new, the Edas Nova.
And that framing is, I think, essential. It wasn't some single, neat revolution. It was this century-spanning explosion of ideas, a true gusher of novelty, as one historian put it.
A gusher that just completely redefined what it even meant to know something.
Completely.
And when you look at the sources, the sheer scale of it is, well, it's just breathtaking. You've got new continents being discovered.
The printing press, which suddenly makes knowledge cheaper and just so much more widespread than ever before.
You've got new stars appearing in the sky through telescopes and these totally new mathematical philosophies that are challenging traditions that had been sacred for, 2 millennia?
Our mission today is to really unpack how this flood of new information didn't just add more facts to the pile. It fundamentally broke the ancient infrastructure of knowledge itself.
That's a great way to put it. Before this, you had this very neat, very defined hierarchy of disciplines.
And if you were an educated person, you had to respect those boundaries. It was all very structured.
Right. So at the very top, you had natural philosophy. That's the big umbrella. It's asking the universal questions, the big why questions.
Why does a stone fall? Why does fire rise? The universal causes of things.
Then a step down, you had natural history.
Right. And this was all about description. It was focused on the particulars, what specific plants grow in this region, what are their properties, often very practical, tied to medicine.
But it was seen as sort of inferior knowledge, right? Because particulars were changeable, uncertain.
Yeah.
Exactly. Not as pure as philosophy. And then you have the third category, the scientia medio, or mixed mathematics.
So things like optics, mechanics, astronomy.
Things that dealt strictly with quantity and geometry. And here's the crucial tension, and you really need to grasp this to get the whole story.
Okay.
In the classical world, math was perfect, abstract. The physical world, messy, imperfect.
So you couldn't mix them.
You couldn't mix them. It was a category error. Using the certainty of math to explain the messiness of, an actual falling rock, that was just not done.
And that division.
Yeah.
That's what's about to shatter.
Completely. And that is where things get really interesting.
To really feel the shockwave of this era, you have to understand the backbone it was shattering.
Yeah.
And that's the traditional Aristotelian framework. It was taught in every single university.
Oh, it was everything. And it was a beautiful, comprehensive system. It was all built on his 4 causes: material, formal, efficient, and final.
And they explained literally everything, from the 4 elements to, a single oak tree. And what made it so powerful, but also so complex, was this idea of the form. For any natural thing, the form, it's like its blueprint. It wasn't just describing it, it was doing triple duty.
Right, I see.
Exactly. The form was the blueprint, so the formal cause. It was the active agent that made the thing grow, which is the efficient cause. And it was the ultimate goal or purpose of its existence, the final cause.
So the whole universe had a purpose, a definition built right into it.
And if you challenge one little piece of that, the whole thing could unravel.
Which brings us to the first great challenge, and it doesn't come from a mathematician. It comes from a much dirtier, more practical place.
The chemical challenge, rooted in the world of alchemy.
Which moves from being this kind of marginal art to a full-blown philosophy of nature.
And this is really personified by Paracelsus. He basically walks into the university system and just tosses out the 4 elements: earth, fire, air, water, that had defined everything for 2,000 years.
An incredible move. And he replaces them
with 3 chemical principles, the tria prima: salt, sulfur, and mercury. He says everything can be explained through these 3.
So he's taking what he sees in the laboratory and making it cosmic. The whole world, the macrocosm, is just one vast chemical retort, one huge lab.
Driven by heat and fire. And this is where the worldview gets really holistic and personal, because of the macrocosm-microcosm analogy.
The idea that the human body reflects the universe.
Precisely. It meant that the philosopher's own moral and spiritual status was crucial. If you wanted to understand nature, you had to be a virtuous, disciplined person. You weren't a neutral observer. You were a moral agent.
Which is such a huge contrast to the next movement that comes along and, frankly, terrifies the Aristotelians.
A mechanical philosophy.
Yes, which is all about the cold, hard logic of space, void, and motion.
And here's a funny twist. Descartes, one of the founders of this mechanical philosophy, he actually agrees with Aristotle on one huge point.
Which is?
They both hated the vacuum. They thought empty space was impossible.
Wait, why? Why was the void so terrifying to them?
Because for them, to exist meant to be extended in space, to have dimension. So if you had an empty volume, a vacuum, what was it made of?
Nothing, by definition.
Exactly. And that just breaks the definition of reality for them. Descartes argued that space was just an abstract way of talking about bodies. If something has extension, it has to be matter. The world was full, no gaps.
But then along comes Isaac Newton, who just says, no, absolute space exists. It's an immobile framework, a stage for action, even if nothing's in it.
And what's so fascinating is the justification he needs for this. It's not just physics. It's theological.
How so?
Newton argued that space has to endure forever because God endures forever. He even famously suggested space was God's sensorium.
His sensory organ.
Like a boundless, uniform canvas where God could act. It's this incredibly deep metaphysical idea holding up his physics.
And the mechanical philosophers even split on how motion itself gets started. Descartes said God's immutability preserves a certain amount of motion in the world.
He's constantly upholding the laws moment to moment. But then atomists like Pierre Gassendi, they rejected that.
What was their view?
Gassendi believed God created atoms with a genuine inherent self-motion from the very beginning. So where Descartes sees God's constant intervention.
Gassendi sees a world that God kind of wound up and let go.
In a sense.
Yeah.
And that one metaphysical difference leads to totally different ways of modeling the universe.
So if the foundations of what the universe is are shaking, then the methods for how you even know things had to change just as dramatically.
Absolutely. You see this shift away from seeking scientia, that old idea of certain deductive knowledge from universal premises.
And a move toward, what? Arguments based on analogy, testimony.
Like the credibility of your witnesses, the consilience of evidence, where lots of separate observations all point to the same conclusion.
So the particulars, the messy details of experience that were once seen as inferior, are now being elevated.
Yes. Historia, the knowledge of particulars, is suddenly on equal footing with philosophia, the knowledge of universals. The facts themselves suddenly matter just as much as the grand theories.
And this gives rise to what are now called event experiments.
Right. And these aren't necessarily in a sterile lab. They were structured observations adapted from really practical places. The workshop, the sick room.
And the absolute classic example of this new method of proof has to be Blaise Pascal's Puy de Dôme experiment in 1648.
Oh, it's the perfect example.
So set it up for us. This is the moment where structured testimony really becomes scientific proof.
Okay, so Pascal wanted to prove that the mercury column in a barometer was being held up by the physical weight of the air. He couldn't just say it, he had to show it verifiably.
He needed witnesses.
And a specific location. So he gets his brother-in-law to take a mercury barometer up the Puy de Dôme mountain in France. And the crucial part is the detailed report. The places, the exact dates, the list of reliable witnesses who saw it happen. It was a practice adapted from the Jesuits.
And the result?
The result confirmed the mechanical view. As he went up the mountain, the mercury column dropped because there was less air above it pushing down. It wasn't magic, it was mechanics. You had to perform the event for everyone to see.
And physicians like William Harvey were doing something similar, right? With the circulation of blood.
Yes, his proof relied heavily on ocular demonstration. Firsthand, verified eyewitnessing, often in a public dissection. Seeing in a credible witnessed context became the new form of believing.
The method for finding causes also had to change. If you were an Aristotelian, you used this complex method called regressus to find a cause per se.
A proper essential cause. The Aristotelian approach was asking, why did this happen? They needed the core essence of the cause.
Can you give an example?
Sure. If a professional house builder builds a house, he is the proper cause. If a group of, say, doctors builds a house for charity, they are only an accidental cause. The goal was to strip away all the accidents to get to the necessary essence.
But Newton is asking a different question.
He's asking, how does this work? He's looking for active and passive principles. He's using geometric analysis to describe how phenomena operates. He famously said that in his philosophy, hypotheses are not to be regarded.
He's trying to get knowledge of causes without just hypothesizing about some unobservable essence.
He's focused on the measurable process. And yet, and this is so important, even Newton, with all his radical new methods, still believed that certain fundamental proper causes, these active forces, must exist. The old and new were tangled together.
So if the intellectual foundations were shattering and the methods were changing, where was all this explosive new knowledge actually being made?
Well, the simple answer is mostly outside the lecture halls.
The universities were still stuck in the old ways.
Stubbornly Aristotelian, for the most part. So if you wanted to innovate, you had to find a new patron, new site. And this pushed many key figures into the world of court and patronage.
This is why you see someone like Galileo leaving a low-paid teaching job to become the court mathematician for the Grand Duke of Tuscany.
And Kepler leaves teaching to become imperial mathematician for Rudolf II. It freed them from the curriculum and gave them incredible resources.
So the courts become these proto-scientific centers.
Think of Tycho Brahe's Uraniborg. It wasn't just an observatory. It was a self-contained scientific city funded by the Danish crown. It was his home, a lab, an observatory, a printing press, all in one.
And patronage also drove very practical things. Princes wanted better military tech, better navigation.
And astrology. A lot of them supported astrology, seeing it as a way to get a political edge.
Then, in the second half of the 17th century, the focus shifts again from these individual patrons to more formal groups.
To the academies, institutions built around collaboration and utility.
So the Accademia del Cimento in Florence, the Royal Society of London, and these were different from the earlier, more secretive groups.
Oh, absolutely. The newer academies wanted to be public-facing. The Royal Society especially was built on this Baconian ideal of creating a new social role for the man of science.
As an independent, modest, virtuous gentleman.
Exactly. They were consciously creating a figure who was not the quarrelsome university scholar.
And to really push that institutional authority, some groups went to great lengths. I'm thinking of the Accademia del Cimento's published reports.
The SEGI, yes. They sometimes suppressed individual authorship entirely. The authority didn't come from a single genius. It came from the corporate body, the collective truth of the experiment.
But maybe the most transformative forces of all were, well, more democratic, the printing press, and the rise of commercial life.
The printing press changed everything. By 1500, there was already a printed book for every 5 people living in Europe. Knowledge wasn't just for a tiny elite anymore.
And you combine that with the coffee house.
Yes. These commercial spots create this open forum. Suddenly, merchants, artisans, professors, they're all reading the same pamphlets, arguing over philosophy. It's sometimes called the birth of public reason.
And this environment fosters things like the Learned Periodical, the Philosophical Transactions, which launched in 1665.
A totally new, rapid way to communicate that just flies across borders and gains huge authority, sharing facts faster than any book could.
And finally, we have to talk about the people who weren't elite at all. A lot of this new empirical knowledge came from workshops, from the home.
The walls between the learned who provided theories and the practitioners who had information, those walls started to crumble.
Right.
William Gilbert credited instrument makers for his magnetic theories. Robert Boyle credited dyers for information about chemical color indicators.
It wasn't just casual, it was often a family business, right? This household model of inquiry.
It persisted for centuries.
Mm-hmm.
You look at a family like the Muschenbrooks. They weren't just scholars. They were specialized instrument makers. For generations, they manufactured the very tools, air pumps, microscopes that defined the new physics.
So the people making the tools were the ones driving the philosophical questions.
They were one and the same. It was a completely integrated world.
So if we try to synthesize this enormous transformation, we see knowledge moving away from textual authority and deduction.
And toward empirical measurement, geometrical analysis, and verifiable observation.
And that shift created these completely new hybrid disciplines. The physical world and the mathematical world merged into what we now call physico-mathematics.
A combination that just a century earlier would have been seen as a fundamental error.
The old intellectual hierarchy was just shattered, disciplines fragmented, methods of proof became diverse and specialized.
And yet, despite all of this change, all this antagonism toward the old systems, early modern natural philosophy remained surprisingly unified by one profound, common pursuit.
A pursuit that connected Newton, the court astronomer, the artisan, and the chemical philosopher.
They were all, in their own ways, relentlessly searching for a better understanding of God. Whether they were trying to map divine creation through natural history or uncover God's unchangeable laws through math, that search for divine order was the great overarching motivation.
And that really does leave you with a provocative thought to end on.
It does. Considering this history, how much of what we call science today is still, structurally organized around that initial theological awe, even if we rarely use the language of divine law anymore.